Section 3.1 is titled Extrema on an Interval. And for starters, we need some vocabulary in order to even be able to talk about what this means, okay? So the first thing we're going to look at is the definition of extrema. This is like the most type I probably ever put on a slide. So taking a look at what I have here. F is defined on an interval I containing C. F of C is the minimum of the function on the interval when it is smaller than, f of c is less than or equal to all the other y values. Okay? It's the maximum when it's greater than or equal to all the other y values. That pretty much sounds like what we mean when we say maximum minimum, right? Smaller than everything, bigger than anything. The maximum and minimum values on the interval are called extreme values or extrema. So when we talk about the word extrema, we mean maximum, minimum values. The ones that we're going to be working with today specifically are going to be called the absolute extrema. The thing that we're going to be doing today that will change in a little bit is that we're going to be working on an interval. That didn't work well. I'll try again. An interval I. So we're not working on the whole number line in general, okay? We're working on this closed off portion of the number line. Like maybe we're looking between 5 and negative 5. So we have definite places where the graph starts and stops. That's unique. All right? So as we do that, we will be able to find these things called extrema. So taking a look at this, we have something called the extreme value theorem. So the extreme value theorem says that if we are in fact closed in between two values, there guaranteed is going to be a place somewhere in between there where it is the largest value and it is the smallest value, right? It's like saying if everyone in this class were to stand up, there is guaranteed to be at least one person in here who is the shortest person and at least one person in here who is the tallest person, right? It's exactly what the extreme value theorem says. It just says it for a graph instead of for individual people. So far, I've talked about what's called absolute extrema. Part of absolute extrema is about relative extrema. All right, so what is relative extrema? Well, relative extrema says that if you have an open interval containing C, on which f of c is a maximum or minimum value, then you can say that C has a relative maximum or minimum at that value. I'm going to draw a picture of what relative extrema actually look like. And there's two different images I could draw. So I'll combine them into the same graph just for fun. So we'll give ourselves an XY axis. And if you have a graph, say that looks like this, it's an open interval because I'm going to go ahead and indicate that the endpoints continue forever. Okay? That makes it open. There are locations where I could sort of draw, I could zoom in. And if I were to zoom in, there is a place in each of those areas where it is the maximum in that area or the minimum in that area. And those areas would be, I thought I had my circle going on, here and here. If we were to zoom in on those spots of the graph, right, you know your calculator does great zooming features, right? If they were to zoom in on that spot, and that's the only spot you saw, you would say there's a place in this interval, in this small spot, where I have the biggest value, or I have the smallest value. Those places are the relative extreme points. So on this particular graph, this one would be the relative max. And this one down here is the relative min. Now, it's not the biggest value on the graph. It's not the smallest value on the whole graph. In fact, this graph doesn't even have one, does it? It doesn't. And the reason that's okay is because it's not on a closed interval. See, this theorem above says that I should have one of these things. But that's actually true if it's on a closed interval. If I don't have a closed interval, I may or may not have an absolute maximum and absolute minimum. But there are these locations where I have relative maximums and relative minimums. So the question might be, well, how do I find those relative places of maximum or minimum values? What's unique about them? How do I identify them? I mean, we can look at the graph of them, but we don't always have a graph. Sometimes we just have the equation. Maybe even sometimes the graph's really difficult to look at, even if I did have the ability to graph it. What would I do to find them? What we look for are called critical numbers. There are two types of critical numbers. One critical number is the one I drew in the last picture. There are locations where, this is a typo, if this is a typo on your sheet, this should say prime, f prime of c. Please fix it if it's not, it's already prime on there. That is a typo. Places where the derivative is 0, or places where the function f is not differentiable. You heard that word before, differentiable. What does that mean?
Derivative.
Yeah, it means derivative, right? It's just another form of the word derivative. Differentiable means it's able to be differentiated or able to find a derivative of it. So we've talked before about places where we can't find derivatives. Where were those places? When were we unable to find derivatives? Sharp turns was one. There's two others. What was that? Asymptotes was one. And jumps in the graph. This one is actually referring to the sharp turns. Okay? And the reason is because the jumps in the graph don't keep graphs continuous, and neither do asymptotes. In order for any of this to make sense in what we're talking about, the graph actually has to have a value there and be continuous there to be differentiable there. So that's what we're looking at, is something that actually has the ability to be continuous. So you can have a graph that does something like this. This is the last one that I drew. Right? So at this location, the derivative is 0, right? If you were to draw a tangent line, what would it look like? Horizontal, yeah? Slope 0. So this right here is a location where f prime of, well, we'll call it c. We'll say that this is occurring at c. F prime of c is 0. And then the other option is that you've got some kind of a sharp turn going on. So this location down here at the bottom right here, this one would be a place where f is not differentiable. Not differentiable there. Okay then, so if critical numbers are these places where the derivative is equal to 0 or the derivative does not exist, then theorem 3.2 says that if we do in fact have a maximum or minimum value, then it has to happen at the critical values. So what we do is we find where these critical values are to see if those are places where we have maximum or minimum values. These are related ideas, okay? So maximum and minimum, relative maximum and minimum values occur at critical points. Now, one of the things you should be aware of is that not all critical points, not all places where the derivative is 0 do this. If you were to draw the graph of, let me give you an example here, y equal x cubed. Does anybody remember what that graph looks like? What does it look like? It kind of looks like it wiggles, yeah? You call it a wiggle? How about like that? Does that look right, Hudson? Okay, yeah. I can see that. You guys see that? It looks like it's wiggling. It's like a snake or something. I don't know. It kind of looks like a tangent graph. It isn't, but it has that same kind of feel. The primary reason it's not the tangent graph is it's not bounded on either side, like by asymptotes, like a tangent graph is. But what I want you to recognize about this graph, it's hard to tell it because I didn't draw the picture as best I probably could have. In fact, I won't even redraw the picture. I'll just justify it with algebra. But the location where it's crossing the x-axis right there, the xy axis, the origin, it actually has a slope of 0 there. Again, my picture's not great. But if you take a look at this equation and you were to find its derivative, what's the derivative of y equal x cubed? Yeah, it's y equal 3x squared, right? And where does that equal 0? When x equals 0. So by definition, there is a critical point there. The slope of the tangent line at 0 is in fact 0. Okay? But that is not a maximum or minimum value of this graph, right? Not even close. It levels out a little bit and it goes right back on up, up, increasing. Does not actually give us a maximum or minimum value. So critical numbers don't always give us maximum minimums, but they give us possible maximum minimum values. Okay? Possible maximum minimum values. So what we're going to do is we're going to have some guidelines for actually finding the actual maximum minimum values. And we're doing that right now on closed intervals. So we will be able to find the maximum and the minimum. There will be definite answers for these. And you could have a location where it has a maximum several times. Think about the graphs of sine and cosine. They constantly hit their maximum and minimum values over and over and over again. So if you had an interval wide enough, you'd have multiple maximum values, right? So we could have that happen too. All right, so to find the extrema of a continuous function on the closed interval, the first thing to do is to find the critical numbers. How do we do that? Well, take the derivative, set it equal to 0, and we solve it. Take the derivative, find out where it doesn't exist. Usually that means a denominator equal to 0, and solve it. All right? Second thing is to evaluate f at each critical number in AB. So if we find out, for example, on this one over here, the one that I gave you, sort of the little off-the-cuff example there at the bottom, I found out the critical number is x equals 0. If I were on a closed interval, let's say my interval went from -2 to 3. That doesn't look like 3. How about I just call it 2? I didn't want to use 2, but that's fine. -2 to 2. So if I only looked at this graph between here and here, from here all the way down to here, and I actually checked out what is, the step number 2 says that I evaluate the original equation at the critical number, I would find out that that's 0, right? Which we know, it's the origin. I mean, I can see it in my graph, right? X equals 0. So that's the step 2, is to evaluate the critical number. Step 3 is to evaluate the end point. Each end point, the end points. So if you were looking over here on this one, that would mean finding the value at -2 and finding the value at 2. So you plug in the end point values. So you plug in any critical values, any end point values, and you compare them. Whichever one is the biggest one is your maximum. Whichever one's the smallest one is your minimum. That's all there is to it. So this section of material really is a combination of everything you've done before. There's nothing in this section of material that's new. Absolutely nothing. You've set things equal to 0 and solved them. You've taken derivatives. You've plugged numbers in. You've looked at things and said this is the biggest one. Nothing in this section is actually mathematically something you haven't done before. But it is sort of pushed together in a way that you haven't done it before, right? Yeah. So let's do some examples. This one just asks us to find the critical numbers. So, critical numbers. Whenever it tells you something about critical numbers, what is it asking you to do? Take the derivative. So that's our first step. Take the derivative. So what is the derivative of x cubed minus 3x squared? Good. 3x squared minus 6x. So critical numbers, you take the derivative, and then what do you do with it? Set it equal to 0. And potentially also find out if it doesn't exist, but these are polynomials, right? So it's never going to not exist. Polynomial functions exist on the whole number line. So how do we solve this set equal to 0? This is now algebra, right? What do you have to do? There's a magic word I'm looking for. What do you have to do? Somebody said it, factor. You have to factor that. 3x squared minus 6x. What do they have in common? 3x. So I'm going to factor a 3x out in front. So if I factor out 3x from 3x squared, what do I have left? X, and then minus what? 2. Fantastic. Okay, what do I do next then? We can't divide, it's a good question. If there were 3, we could do it. But we don't want to divide by a variable because we'll lose solution. So what can we do instead of dividing by the 3x? It's been a long time since algebra, I can tell. Maybe you guys need to stand up and do some jumping jacks. You seem a little tired today too. Well, we're going to set each part of this equal to 0. Right? The only way these two things multiplied together equal 0 is if one of them equals 0. Not both. They don't both have to be, but at least one of them has to equal 0. So we have 3x equal to 0, and we have x minus 2 equal to 0. So what's the first x value? 0, because now we can divide by the 3. What's the second x value? 2. And these are your critical numbers. Okay, just algebra at the end. Extra steps, set it equal to 0 and solve. A lot of times that means factoring. Not always, but a lot of times it does. Okay, so now we're going to use this idea of finding critical numbers in a broader sense to actually find extrema. Find the absolute extrema of the function on the closed interval. And step number 1 in finding absolute extrema is to find what? Critical numbers. So step number 1 in what we're doing, I'll kind of number them as we go along, you don't have to, but is to do what we just did on the last problem. So that means finding the derivative. So what is the derivative of negative x squared plus 3x minus 5?
Negative 2x plus 3.
Negative 2x plus 3. What do I do next? Solve. Can't solve just yet because I need to do something before I can solve. Set it equal to 0, and then I need to solve. You're right, yeah. You were just already ahead of me, weren't you? Yeah. All right, this one I don't have to factor, right? It's a linear equation. So, did you say that's good? Oh, God is good. Yes, he is. All the time, right? Absolutely. All right, so what's this going to be? Yes, it's x equal 3 halves. So if I move the 3 over, it moves over as negative. Divide by the negative 2, they end up with a positive, so this is 3 halves. This is one of my possible locations of extreme values. Possible, right? What does step 2 say I'm supposed to do with this value? Evaluate it. Into which function? The original one, right. We don't want to put it into the derivative because we just get 0. I mean, that's how we got it, right? Would be unproductive. We're going to evaluate in the original function because what we're really wanting to know is what the y value is there. We're going to compare those. So if I plug this in, and you guys are going to do that in your calculators or in your head or something, we're plugging in negative 3 halves squared minus 3 times 3 halves, and then minus 5. And for the most part, when we have the ability, and we almost always do, to do so, we're going to leave it in fractional form. And if you're not sure how to take this in your calculator and put it back into a fraction, I can show you how to do that too. So you got negative 5.25, and then let's turn that back into a fraction. So if on your screen right now it says negative 5.25, and you hit the math button, like it's showing up with that. Did you get a different number?
I said negative.
Why is what negative?
Minus.
Oh, because it's a typo.
That's what I was.
Oh, is it wrong?
Yeah.
Okay, we'll try again. I want to slow down. You guys can find me the value again.
Negative 11.
11 what? 11 fourths. And negative. So in your calculator, it probably said something like negative 2.75. Okay. I just want to make sure everybody knows how to turn these back into a fraction before I move on from this one. So let's say your calculator spits back out at you the decimal, negative 2.75. If you hit the button that says math, the very first entry next to on that menu that comes up says frac. Just select that option and it will, and hit enter on it. Hit enter back in your regular screen. It will turn it back into a fraction. Are you good with that, Nate? Did you find it? Yeah? Okay, fabulous. So this is our value. It's not bad for us to keep in mind both versions of it. because we're going to have to compare this in a moment to some other values. What's the third step? Evaluate the endpoints. So the endpoints here are the -2 and the 1, right? Into which function? The original. So I need f of -2. So this is -2 squared plus 3 times -2 minus 5. You don't have to write that out, but that is what we're plugging it into. What value do you get? -15. Is that what you said? Does that look right to everyone? Okay, good. We have one more. We're going to do f of 1. So we have -1 squared plus 3 times -1 minus 5. What does that one give us? Negative what? -3? I'm getting something different. Did I put something in wrong? What did I put in wrong? Oh, it's a positive one. Okay, now I might get a positive. Okay. So now what do we get? Negative what? -3? Yeah, that looks right now. Okay, we all in agreement? Awesome. So what's our goal here? Well, step 3, our goal is to compare these three numbers. Those are the y values of our function at these particular x values. We'll start with minimum. Which one is the smallest? -15, right? It's definitely the smallest. So it says find the absolute extrema of the function on the closed interval. They don't exactly indicate what we're supposed to be giving them. Do they want the y value? Do they want the x value? Do they want the ordered pair? They just say to identify it, right? So you may see WebAssign actually, I mean, they'll tell you something. They'll probably write down x equals, or they'll put the ordered pair notation or something like that. So for what I'm going to do right now, I'm going to say that we have an absolute minimum, and the absolute minimum value is -15. Okay, the absolute minimum value of -15, and it's occurring at x equal what? What x value does that happen at? I think that one was -2, wasn't it? -2. You also might see that it written like this. You might see it written, and I'm fine if you did this, and it's an absolute minimum of, -2, -15. That's the absolute minimum location. That's sort of thinking of it as an ordered pair and like on the location value itself. The first line where I wrote it right here is thinking about it more like context of a problem. You know, the absolute minimum profit or something like that is -15. You know, something of that version. So let's find out what the absolute max is now. What is the absolute maximum value? So comparing all those three, which is the biggest one? The -2.75. So this is an absolute maximum of -11/4 or -2.75, which is fine as long as you actually have a terminating value. Don't round things. At x equal what? 3/2, I think, right? Wasn't that at 3/2? Or again, you could say, if you're thinking about it in ordered pair notation, this is an absolute max, which is 3/2, that's my x value, -11/4, which is my y value. Okay, is that all right? Okay, we're going to do one that's a little bit messier. Why is this one a little messier? Because what is it, Evan? Oh, but you didn't tell me the why. It's got division in it. So when I do the derivative, I'm going to have to use the quotient rule. You got it. All right. So step number 1 is all about finding derivatives and setting them equal to 0, yeah? And again, if you don't like the letter t, switch it to x's. That's totally fine. Y'all know how to do the quotient rule. You do. And you're going to be tested on Friday, so if you don't yet, make sure you do by Friday. Somebody help me out with this. What will the quotient rule, all written out long ways, what will it look like for this? The bottom, t minus 2. Derivative of the top, that's 1, right? And then it's minus the top, which is t, times the derivative of the bottom, which is 1 over t minus 2 squared. And then I have to clean this up, yeah? Make sense? So how does that numerator simplify? It is just negative 2. I get t minus 2 minus t, which is negative 2, over t minus 2 squared. Okay, so here's the deal. We're supposed to set this equal to 0, right? When does this equal 0? When what? Right. In general, a rational function will equal 0 when the numerator is equal to 0. So when does this numerator equal to 0? Never. It's a constant that's not already 0, right? So is this ever going to equal 0? No. However, could we set this equal to something where it doesn't exist? Sure. When will this function not exist? At what value? What t value will make this not exist? Yeah, say it louder, Tyler. 2. What's wrong with 2 here? You get a 2 in the denominator. When we put the 2 in, we get a 0 in the denominator, right? That's a problem. T equal to 2. Now, the reality is that in step 2, when I sort of try to plug in t equal to 2, what happens? It doesn't exist either. What's going on in my graph there? There's an asymptote. In chapter 1, we talked about it as being a non-removable discontinuity, right? Can't get rid of those asymptotes. So do I really have a critical number there? I mean, I do, but is it going to give me a max or a min? No, because it's actually a value that my function doesn't even exist on, right? It doesn't even work. All right. However, I do have the closed interval, and actually this is an interesting fact as well. Notice this closed interval is from 3 to 5, and notice what kind of value this is. Actually outside the interval anyway, isn't it? It's not in between 3 and 5, so it gets eliminated for that fact alone. We still have to do step 3. What was step 3? What's step 3? Yeah, to check out the endpoints, right? So we're going to evaluate these at the endpoints, which is h of 3. And then we'll do h of 5 in a moment. So if we put in h of 3, or put in 3, excuse me, into the function h of t, what do we get? Yeah, 3 over 3 minus 2, which is, man, my handwriting, it's not my handwriting, it's this app. That's better. All right, this is 3, right? And if I plug in 5, what do I get? 5 over 5 minus 2, which is 5/3. All right, so this is an absolute max of what? I'm sorry, min. We started with min last time. We'll start with min again. Absolute min of what? Which one of those is smaller?
5.
Yeah, the 5/3 is smaller. Absolute minimum of 5/3 at x equal, or t equal, because we use t here. T equal what? 5. And there is an absolute maximum of what? Of 3 at t equal to happens to be 3. Again, you could also write it with the notation where you wrote it as an ordered pair. Unless you're told otherwise, that would be fine too. Okay, so in this one, it just is the endpoints. There's actually nothing in between that works at all. That's a possibility. All right, and what lesson would be complete without a trig example, right? Absolutely. I just saw Miss Dodgen, Kate. I just saw her teach some trig, so we should definitely look at some trig today too. All right, so here's our example, last one. G of x is 3 cosine of x, and the interval is 0 to 2 pi. So somebody tell me, what is my step 1? Derivative, right. So what is the derivative of 3 cosine x? Yeah, negative 3 sine of x. It's fine for you to write the 3 and then the negative sign as long as that negative sign were in parentheses. You don't want it to look like subtraction, right? Don't make this look like 3 minus sign. That's not what you have. All right, so there's this one. What am I going to do with this derivative now? Set it equal to 0, which then starts to look like a unit circle problem. It's not a hard unit circle though problem, okay? What am I going to do with the negative 3? Divide it, right? And if I divide it to the other side, what happens? Yeah, it goes away. So in some sense, I'm sort of ignoring it. This is going to be equal to 0 when the sine of x is equal to 0. So unit circle, between 0 and 2 pi, where do I get sine values of 0? 0 and pi and 2 pi. And so it happens to actually be, and this is just because of the interval they gave us, it happens to be that the endpoints are 2 of these locations as well, right? It just happened to work out this time. So it's almost going to look like we're not going to do step 3 because within step 2 I'm already going to find those values. Step 2 is to evaluate these points now, right? What was my function's name? G. So we're going to find g of 0, which means finding 3 cosine of 0. So what is 3 times the cosine of angle 0? That's 3. Cosine of 0 is 1. Now we're going to do g of pi. So it's 3 cosine of pi. What will that give me? Negative 3. Very good. And the last one, g of 2 pi. 3 cosine 2 pi, which would be 3 again. Yeah. Right. And then I'll just write this down to remind ourselves that step 3 is done already. Because it would be finding the endpoints, which was g of 0 and g of 2 pi, right? And we already did that. So, we are ready. What is our absolute minimum? What is it? It's negative 3. And it occurs at x equal to what? Pi. And the absolute maximum is what? 3. And this one actually occurs twice, at x equal to 0 and at x equal to 2 pi. Any questions?